Hello, hello. So before we start with the lecture, I'd like to let you know that the location for our happy hour has changed. So instead of Pau d'Arco, it's going to be the same bar that we're going tomorrow, okay? It's a cash bar, and they're going to play live music tonight. It's going to have a lot of fun. Monarca? Eu falei o quê? Monarca. It's the same bar that we are going tomorrow, okay? Huh? Is that walking distance? 1 kilometer from here. So, Uber or taxi? O título é aquele lá? O título é aquele lá? O título da sua palestra é aquele lá? Não. Falar biomecânica. So let's start with the lecture of Professor Fabiana Nunes. Costa, desculpa. Costa, Biomechanics in Pterosauria.
Well, hello. It's a pleasure to be here today to talk a little bit about a research line that we have been developing at our lab. It was supposed to be a roundtable, and I will try very hard to fill this gap because Habib's not here. So I have implemented a little bit my presentation, and hope you can enjoy it. I will try to talk a little bit about the advances we are having with our studies and at this particular field research. So I gave this other title that is gaining ground on biomechanical studies, from movement simulation to AI-assisted 3D modeling pterosaurs. So let's start to, let me see if I handle it properly. Wow, no, not working. But I can. So, let's go. I have three main questions that I'd like to put here to guide this presentation. And the first one is to what extent have we advanced on this field study so far? So I'm going to try to present the beginning of this field research and what we have achieved so far. So, and what are the problems that still challenge us at this field research? And there are a lot of problems still, because of course we are dealing with computational softwares, and we have to learn how to deal with these advanced technologies. It's not an easy thing. So, and what are the future perspectives for pterosaur biomechanics? So I will try to discuss a little bit about these questions and try to give not answers but debate over this issue. So I think we can start discussing on how or when these studies have started. What was the genesis of it? And I can say that we started like this. Yes, it's a puzzle. And it's what we have at the beginning, because we have a bone and another bone that articulate with each other. So we didn't have computers, we didn't have software, so we had to manipulate it with our hands. So we fit one bone into the other, where they articulate and move. And then we try this range of movement manually. So this is, of course, this is not a pterosaur. It's just to illustrate the problem. So this is the research E1 Fordyce and the penguin. But this worked like this. Not anymore, of course, but at the beginning it was like this. Had to put all together and try these movements. So that was the challenge, manually. So, okay, we have advanced so far, but that's an important question that we can make. That is, what kind of information has been refined with advances on this field research specifically? Well, I have some a practical study case that I can put here that was issue, the specific issue of my master dissertation. When all of this began, all my interest was raised at that time at Museu Nacional when I started with Alex. And the question was, what was the stance of this particular pterosaur? This is Anhanguera piscator, genus Anhanguera. And at that time, we had two main hypotheses that defended that pterosaurs or pterodactyloids, not specifically Anhanguera, but they could be quadrupeds or bipeds. And that the first hypothesis was guided by Kevin Padian, in the beginning of 80s, that defended that pterosaurs was biped, and the other was by Wellhofen, that defended that they were quadrupeds. And this question relied upon a very specific issue that was the prepubic plate being closed or more open. Like, oh my God, let me point. I think this one is working. Okay, thank you. Here, if it's closer to each other, we bring these bones down the main line of the body, and then we have a more erect stance, a biped stance. And on the contrary, we've considered these blades a little bit opened. Then we have a more spread stance. These bones are spread, related to each other. And then we have a more spread position, a quadruped position. So, what was our question for Piscator? Was it a biped or a quadruped pterosaur? So, we wanted to test it mathematically, three-dimensionally. That was never been done before. It was at the beginning of not at the beginning, but yeah, I can say that was at the beginning of these studies. So we go from this to this. We tried something different to answer this question. So we modeled specifically the pelvic girdle of this pterosaur. And this is the pelvis and part of the femur, the femoral head articulated with the acetabulum. And then the forces that were considered here, we worked with lever arm formula to test it. So according to our results, we had repositioned the leg. And then from this, we came to the result of this pterosaur being a quadruped pterosaur. So and it was considered like this, and so far so good. For now, it's not being contested, refused. For now, it's okay for this because it was mathematical. I will talk a little bit later over this issue again, just to illustrate how have we advanced some of these issues with biomechanics with 3D modeling and computer software. So let's talk a little bit about the genesis of this modeling. So it's important, it answers questions that are very important questions in this field of movement regarding pterosaurs. But how did this start? So, of course, all of you, we know that tomographies, and it is still used, of course, nowadays, but it's not a recent innovation. It started being used early in the 20th century, so not quite recent, but it was a technique used at that time. And this is the tomograph that was used. This yeah, that's it. Just manual, of course, and you had to operate it. I don't know how, but yes. And William Solas, the geological polymath that began the task of manually grinding away fossils embedded in rock, and he took images like this from this machine, this very basic machine. This is the genesis of tomography, and so he was able to produce 2D slices to create physical models of specimens out of wax, cardboard, or polystyrene that was material used at that time. So this is William Solas. And of course, at that time, it was an extremely time-consuming technique, extremely time-consuming. To have you an idea, this is Eric Jarvik. Of course, this is not a pterosaur, but it is a 3D wax model of Este, It's a Devonian fish. And it took this researcher to produce this 3D wax 25 years. Years. So, of course, we don't have this anymore. We can produce things much more advanced like this. Yeah, you have seen a lot of very nice and interesting biomechanical studies here in the morning from our colleagues. And it's very nice to see that this campus is advancing here in Brazil. And we have such nice pictures like this, internal airspaces, I think, from Thaisa and Richard. Richard, did you take 25 years to do it? No, of course not. So you have this, and this nice, beautiful force distribution, of course, at vertebra, and even muscle reconstruction. So we was from that to this. Nice work. And now we have a lot of techniques of 3D modeling in paleontology. This is a table of not quite recent work, but somehow from Cunningham and colleagues from 2014 that list a lot of these techniques, and it's interesting because you can see here, of course, the resolution, if it's destructive or not, but it's interesting here, the cost to buy or use it. That's a very interesting point that we're going to comment because, yes, you have to deal with this problem. Some of the equipments are very expensive, so we have to be financed. It's a financial support is demanded. So we have, of course, from photogrammetry, that I will comment, and it have already been commented here, but it's a technique that you compile photographs into a 3D model. It's a manual technique, but it's quite accessible and not so, the cost is not high. You have to have a good machine, a good equipment, but it's quite accessible. And we have other equipment that it's not so cheap or more expensive, like micro CT and tomography scanning, and others that it's not so accessible at all. And in synchrotron, that is the top, the most distant from our costs, because we have here in Brazil, and we have to. It's not. You don't buy it, so you have to go to a specific place to work with this technology, and it's not accessible, of course, but and not portable, of course, either. So it's a list. Of course, we have a lot of these techniques available. It depends on what we want. to choose one another and important what we want, especially. So, and the softwares, a lot of softwares are available. Some of them are free, some not. We work with some of them, for animation, visualization, Auto, Maya, and Blender. For 3D mesh and conversion of formats, Mesh Lab. I think I'm too close to my... Okay, let me try to... Okay, and the finite element analysis, we use ANSYS, but there are a lot of techniques for it. And computational fluid dynamics, we have a specific work, a master dissertation at our lab working on fluid dynamics, and we work with ANSYS. But there are a lot of softwares, and some of them are free, some are not, but they are there, and we can work on that. But we have to learn how to deal with it. It's not easy. So we have a preparation to deal with these technologies. So that's what I have just said. Biomechanics does not deal with just 3D modeling and advances on computational software. That's still a difficult thing, but we have to deal also with the forces to which these models are submitted to work. So we have to learn a little bit of physics. We have to count on engineers, mathematicians, whatever, to do these works, because they are not easy to be developed. So Alexander in the 60s said that these mechanical engineering systems must balance the applied forces with the material properties and dimensions, morphology. And in biological systems, this is a compromise between the forces imparted by muscles, the structural properties of bones. So have to deal with a lot of things. So the problem of technology is just one issue we have to deal with. We have to deal with this game of forces and everything that work during flight that the animal is submitted to. So this acquisition of models, of 3D models, we have, as a result, different virtual models regarding resolution. And it depends, the software that you use, how you're going to do it, depends on the investigation, of course. And we have basically these three techniques, like I think I can say like this. And we have the photogrammetry that I have commented, that structure from motion photogrammetry, that allows the recreation of fossil surface in 3D using photographs. So if you have a good equipment for photograph, for taking photographs, it's fine. It's very accessible, like I said. And it's a completely automatized by specialized software. So you take the photographs, there's a software that joins these photographs together, and then you do a command there, and it joins everything to produce a virtual model. And there are softwares that do it, like Agisoft, Photoscan, 3DF, Zephyr, and others. There's the 3D laser scanners. There's a more automated technique with resolutions. It's more refined technique, but you can control the scanning resolution, but it's automatized, it's not manual. We just got money to buy one for the lab, a manual one. You do the work of manipulate it, but the scanner do everything. All the capture of image capture, the scanner do it. And there's the computed tomography. Like I said, the tomography, we still use it. And it provides more detailed reconstructions of samples through the acquisition of series of sliced structures. That is the tomography, the principle of tomography. But, as I said, the first problem that you want to work with biomechanics. So the first problem, I have to study physics. I have to learn, of course, the pterosaur morphology to understand it. No, I think the first barrier is cost, because it's very expensive. It can be very expensive, or not, if you use photogrammetry. But for some things, you have to use other things, other equipment, other softwares, and it's expensive. So quite expensive equipment, depending on what you are investigating. And another problem is the high demand of human resource formation, because we are biologists. We are not mathematicians, we are not engineers, and we don't use to deal with numbers, formulas, and things like this. So it's difficult, because you can produce your model. Well, the model is here, so now what? Yeah, I had to put it flying, but so what forces? And the fluid, the dynamics, and whatever. You have to understand what's going on. You have to find out the formula that you have to apply, and so you have your results. So we try to do these partnerships at UFABC with the engineers, because there we have engineers so strong there. So we have the people that deal with airplanes and biomedics. So they help us a lot sometimes when we need. So other problems, I will talk about them. So of course, biomechanical modeling is an important and powerful tool for quantifying the evolution of functional performance in extinct animals. And then we understand this anatomical innovation, the selective pressures driving major evolutionary radiations, like Broyd and Collab said. But what we have in fossils, that's another problem, because we basically have hard parts. We don't have soft tissue, nothing like that. Sometimes, but never, of course, complete. So we have to reconstruct soft tissue in models. There are techniques for this. And, of course, these reconstructions, some people question these reconstructions because they say that we have to validate it on extant animals, etc. But there's, can be a problem like this. This is a quite recent work that have been studied at evolutionary biomechanics, hard tissues or soft evidence for Broyd and Collabs, and they question these things, that we have to validate these studies with extant animals, and that just 35 studies like this have used the methods of numerical soft tissue reconstruction to validate with extant animals, blah, 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 but other problem. Modern analogs to be compared with. Of course you use, and you use birds and bats, but yeah, there are still problems with this. And of course we have no extant pterosaurs. There's another research line that I work with. It's a behavior of extant animals with Xenarthra. Nothing to do with this, but I also study the extinct armadillos, and we have to, with this group, we can establish a parallel with extant and extinct armadillos. It is much easier, but we can't do it with pterosaurs, of course, no. But of course, what's the answer? Not do it? No, we do it. With what we have, and this is what we have. We have birds and bats for these analogs of to deal with these questions of flight and whatever. So this is a one work of Wheaton and Habib that work with size and flight diversity of giant pterosaurs using birds as analogs, and others. You will find that literature using birds and bats, for example, integration and dissociation of limb elements in 5 vertebrates, a comparison of pterosaurs, birds and bats, from Bell and Collabs, and this one is quite new, from 2022. How did extinct giant birds and pterosaurs fly? So we use birds and bats. Yes, this can be a problem for some issues, but we have to use what we have. And this is what we have. And of course, questions appear to try to minimize these problems or question it. And this is a question of taken from the work of Witten and Habib. Are birds suitable analogs of giant pterosaurs? They themselves asked this. So, of course, some aspects, it's not unreasonable to assume that some aspect of bird and pterosaur flight should not also be similar. Of course, it's quite obvious. And of course, it's questionable. But, again, it's what we have. So, we have to deal with it somehow. Another problem is that, of course, fossils are incomplete. This is the standard situation. It's often partial, modified by taphonomy, or lacking modern analogs. So, which can have confined many studies to descriptive and observational techniques. So, problem number 3, usual deformed material. That's a problem. We try to minimize it with the softwares, with reconstructing these broken parts in the computer. So we have also, of course, to know a lot about the morphology of the animal you're trying to build at your virtual contest. And what can we do to mitigate, to minimize this taphonomic distortion? One thing is assuming symmetry to complete a partial specimen, and we are specifically trying to work on this aspect with AI. It's quite new, and we are just, it's just in the beginning, but it can be a very interesting thing if we succeed. Using modern analogs as guides, as I have just said, we use what we have. Forming composites from multiple individuals, we have problems here, so, but it can be done. And reconstructing morphologies mathematically, or addressing biomechanical properties through mathematical formulas. It's ally math plus 3D modeling. That's a trend also. So I will discuss some of these things with our works. This is also a quite recent paper from, I think, last year. Yes, last year. From engineers, that updating studies of past life and ancient ecologies using defossilized organismal proxies. So that's interesting because I have been reading these things because as these people work with these softwares, they, of course, point some of the problems that we can deal with. So, of course, they say the virtual model does not stand alone. And again, they defend that we have to validate our digital models with existing physical models. So this put another step on our study, that is, when you have the virtual model, we have to print it in the real world to work with it together to validate what we are trying to experiment, I don't know what. So that's not quite usual for us, but it's a point of view. And so they defend the 3D printing, for example, to convert, to go back and then convert the virtual model to the physical, to a physical model. So you can submit this model to forces in the real world. Yes, something we can try to deal with, but it's not common. And they question about they talk about the comparisons and the question about the properties of the material being used. And of course, it is a problem, a bigger problem for groups that we don't have clear modern analogs. So this is a thing that we are studying, of course, to see how can we deal with it, according to the engineers, of course. We are doing what we can for now. It's so far so good. And this is a very interesting workflow from this study that lists points for every single step of this process, and will point specifically where are our problems. As I said, this reconstruction in with-through deformation, because our material is broken, deformed, crushed, etc. And so we have the fossil specimen, of course, but that's the first barrier here. We have to put this model in a way that we can study it. They are mostly not prepared for it. The modern analogs. So when you validate the use of modern analogs, depending on the group, you can have some difficulties dealing with it. And the comparison of virtual and physical results. But we have to have the physical model to compare the results we achieve with this model in the real world. So I think basically these are the problems that we face when we do this process to try or experiment or model in some contest, some virtual contest, depending on the question. So, some examples of the problem of deformed specimens for biomechanical studies. For example, this is our study from 2021, where we have to estimate the cross-sectional area, the CSA, but these can be only estimated for a limited number of pterosaur taxa due to taphonomic limitations. Again, some specimens are laterally flattened or crushed, so it's a problem. So it limits us a lot. So you can realize that most of the species that we have being worked with biomechanical studies are three-dimensionally preserved, etc. That was 2D preserved, crushed, flattened, are not. We miss a lot of these kind of studies, so we are trying to fill this gap somehow. And this is a limitation that we find in works like this. Determining the quadrate inclination in distorted specimens is a problem because working with this problem, the inclination of quadrate match the mean direction of jaw adductor muscles. So if you don't have it, you have a distorted specimen and whatever, you can determine this inclination, so you can't reconstruct this muscle. So this is a problem. And then you cannot work like this and have this lever game here to study the movements that these schools are capable of. So that's a problem. And of course, another illustration here to show this. The occipital region and the quadrate are nearly vertically directed. And when you have this, it indicates a high-angled orientation of this muscle, external adductor muscles, like in Aneurognathus. So the range of this aperture, can be almost a 90-degree angle, but it depends on this reconstruction of this muscle, this reconstruction, this position that is limited to somehow good preserved specimens, and then we can study these maximum, this optimum, maximum gaps, the ranges of movement, and in different pterosaurs, when we have them well preserved, of course. This work of Henderson worked with it and determined these angles for a lot of species, pterodactyloids and non-pterodactyloids, but again, how to determine the unflattened specimens? That's the problem. And taking this assumption that we are just studying the well-preserved specimens, we are trying to, at the lab, work with two-dimensional specimens. It's just the beginning. It's a very preliminary study at this now, but we are going to advance, I think. So, of course, the problem is quality of fossils, like Henderson says, when worked with it specifically, and the two-dimensionality of these fossils. So it hampers reconstruction of more accurate model to work at this virtual context and do the biomechanical studies. So this problem, and of course we have this issue that the schools of pterosaurs are frequently preserved in lateral view. So we have this challenge of converting 2D specimens into 3D models. That's what we are trying to do. So we use, of course, for this in some specimens that are not very well preserved, we infer these broken parts from nearest relatives, of course, but we are really trying to study those specimens that are two-dimensional, indeed, that people don't study. Let me see if I can cope with it. This is some of our models. Okay. That this is a student of ours that working with biomechanics and terrestrial locomotion in Pterosauria, and she's doing some of models that we are going to work with. This is a pelvis and femur reconstruction of Tupandactylus. Of course, she is trying to put the model ready to simulate the situation that we want to simulate. She's doing a manual work of converting the 2D mesh into 3D mesh. Henderson had to deal with this question also, and he developed the mathematical slicing method to distort these specimens, and he worked with some of them, and they were, I think they were reasonable. But this is a work of 1990. So onwards, what we have, indeed. So we are trying to learn, of course. This is very, very, very new. Artificial intelligence, the AI. And they are using the artificial intelligence that is here. It's trying to, it's learning from us and teaching us a lot of things, and we are trying to use it to favor our studies on biomechanics of pterosaurs. So to construct a 3D representation from a single image representing an object in 2 dimensions. So we are going to tell the machine, this is the photograph I have, please produce a 3D model for me. To sum up, it's this. So we have to teach the machine how to do it. So this is the challenge. A huge challenge. There is a quite recent work, this one is from last year, that authors used it to artificial intelligence in paleontology, and I was studying this research article. They did with Nuhaki's way, but the problem is that they didn't tell at the article the method they used to reconstruct it. They got a very nice result, but they didn't teach how to do it. So have to. So the purpose there, this article, is to it's the digital protection of the whole biota. It's for exhibition, not for research purpose. And this was the studied specimen. You can see that it's a complete two-dimensional species, flattened. How can we study the biomechanics of this so nice individual? It's a challenge that we are facing. So they there said that they create a line drawing based on the specimen and it generated a restored 3D model. So from this they depart from this to this line drawing. That this is a thing that we do in our papers. And they are just trying to deal with fragmentary specimens. And they use these comparisons with closely related taxa. This is not new for us, we do it. And they reached this result like, wow, I want this. I want to teach the machine to reach this. I don't want to manual model it. I want this. But the problems that the article did not mention, the technique used, the methodology, I guess they did it manually, some pieces of it. I'm not sure, but they didn't teach how they give this command to the AI. So we have to learn it, and we are talking to the engineers that at BBC to try to learn it. And we try to do it with the same species to test. This is the study of our student there. That is the development of three-dimensional models of fossil vertebrates. We put fossil vertebrates, but it's pterosaurs, using artificial intelligence for enabling biomechanical studies in vitro environment of 2D specimens. So we try to do it like they said. We put the line, and this is manual. We put a pen and the virtual pen and to put the drawing, the silhouette of the pterosaur, and we had this. This is what we had, the 3D silhouette. Perfect. Well, of course, this is just a trial. It's not so good, but it's good. The scope is here. And the technique, what we are trying to reach is develop this mirroring technique. That is, you mirror one side to the other. So you have a complete model. You reproduce the opposite lateral view and add volume to the object. We are working on this premise. And this is what we are being guided for it. Trying. We use this software, Monster Mesh, that create these models. And of course, I think we are not going to stop the manual work, but the purpose here is to reduce it at the maximum level, so the machine can produce it, but to optimize our time. So we are trying to teach it to the machine. But there is a problem that we detected. The technique adds at least this software. We didn't try the others. We are just in the beginning of the study. But there's a standard volume that the AI, the problem is the machine thinks, or I don't know, it knows better than us. That is the reality. It knows better. So we have this Tupandactylus navigans, and we took the photograph, a picture. It's from the internet, not from the specimen. And we exported to this interface of the software and talk to the machine. Please produce the model. I want a 3D model of this flattened specimen. I want to work with it biomechanically. But there is no, of course, we are still studying, but it adds a standard volume. Of course, the machine doesn't know how the school of Tupandactylus is, but we are trying to teach it, but it is a problem because we have to understand this interface to put these numbers, because I think light is not it's not very good to see it, but if you can see it laterally, it's perfect, but it's kind of inflated here. And if you manipulate it, of course, it's just a print, but if you manipulate it, you can see that it's inflated. That's not the school of Tupandactylus, it's not inflated. So we have to know how to tell the machine that the skull is kind of flattened with few volume to have a model that is, of course, similar to what we have. So we have to, so we can biomechanically study it, whatever the question is. Of course, we can work in the software with these ready models, 3D models. We exported some of them, like this, the Parapcephalus purdoni, at these sites. That we have a lot of models, 3D models there, and we exported it. It's quite good, but it's not produced by the machine, but just imported to the machine to work at this virtual context. It is so far so good, but it's not what we actually want. We want the machine to create it for us, but I think we have to advance a little bit more going onwards. So we're still trying. So another studies on our lab is just now to give examples of what we are doing. There's this poster here, so I'm not going to talk more about it, but we can use math. In this work, it's just math to, for example, determine the athletic capability of pterosaurs. So it's an index, it can answer a biomechanical question. How was this athletic capability of pterosaurs? And it's calculated. These are the formulas. And it's a master dissertation that's going to be defended this year of this student. He's not here, unfortunately, he couldn't come, but it's an interesting work that we just worked on formula, not models, not 3D models. And produced that, and he worked with this pterosaurs, and basically literature data. And that's the importance that we have these numbers and tables in the articles, so we can do works like this using math. And he established these indexes and some graphics showing this variation between humerus and femur and their relationship regarding body mass, etc., to have the result on the athletic capability of pterosaurs. And he reached the result that all pterodactyloid pterosaurs share high values, or I also have this in capable regarding this index, indicating that not only the Asdakid possess extraordinary resourcefulness in land locomotion, others as well. So it's a quite interesting study. It answers a biomechanical question, and it has nothing to do with modeling. So we can, I think it's the cheapest process. It's just using math. There's a quite new trend in paleontology. It's paleomimetics. You have to learn all of it because this is very, very, very new. Applying nature's process and fossil materials in the real world. So it's using pterosaurs or whatever to inspire objects in our real technology. There's this recent paper of Martin Silverstone et al. That deals with this question, that fossil forms can provide platform structures and integrated systems that can contribute to next generation aircraft, robots, etc. So it's a very interesting thing to use to get financial support for some things. So it's very interesting. And of course, we have a lot of possible achievements regarding pterosaurs, flight, inspiring control and wings. If we learn how pterosaurs, this quite bizarre animals fly or whatever, walk, it can inspire our technology, our planes, etc. So it's a trend in modeling also. So, of course, engineering partnership demanded. It's specifically in this issue because it demands the construction of wings and other things that are inspired in these animal models. So it's, I think it's a very promising research field. That's another work at our lab that our student, Greg, he studies the analysis of the influence of cranial crest on the aerodynamics of Tupuxuara leonardi. And he's studying basically fluid dynamics. So basically fluid dynamics is in the biomechanical analysis to understand how ancient organisms move that copes on simulating fluid flows of liquids or gases. In his case, gases, because it's flight. And we are working a lot with cranial crests. So this is the specimen. And the Greg William Massey dissertation is another student's dissertation, Welton, that's working on mechanical performance testing of the school of Tapejara Hofeni through FAIR. So we are working a lot with pterosaur crests, these bizarre and quite different structures of pterosaurs. And we are at this producing model phase. So here is the prints, just you to know the interface of the study. Here is creating the 3D model of the school by Angisoft Photoscan Metashape, and here are the photographs. I think here he used photogrammetry to do it. The final 3D model of the school of Tupuxuara leonardi. Here's the interface of the school from that real model to the virtual model at the virtual contest. And here is the possible geometries that he is studying at Blender. This is the crest as it is. And then there is this representation of minimum and maximum crest to test this mechanical functionality. So this is the work, and he submits these models to wind tunnel. So this is the wind tunnel, the creation of wind tunnel domain features, and he is at the step of start the simulations at the wind tunnel. So perhaps next year we can bring these results ready at another congress. And so here's just to understand the interface, the calculus of the flow. This is the mesh, the domain, and the subdomain. We have to put the model here and try to understand how these forces react, this flow, the behavior of the school in this flow, and the pressure and whatever. So we are just at this step of trying these forces at the model. This is details of the domain division, that and the interface. This is very, very technical, so just showing. And the pressure distribution of flow through the cranial crest of Tupuxuara. It's the first experiments when we submitted the school at this wind tunnel, the pressure of the air, and then we're trying to understand how the school behaves in this process. This is one of the graphics that we have of the press in, the incoming, the behavior of the school with the incoming air pressure. in this domain. So for now, that's very, very, very preliminary, but for now, we have a stability of the school being positioned approximately at 50 degrees. So, but it is very, very, very preliminary. I'm not talking about it right now because it's just to show how it works, minimally. And this is the other work of FAIR. This one we just, at this moment, we just have the model, not the simulations, but we are just advancing to this step now. And we are working with of course, Welton is working with the crest of Tapejara-Velhofer, with FAIR. So these are the models, the first models that he has created. The final 3D model to be tested, here in mesh, and here in the solid, it's a solid surface. And with different colors and distribution of force. And here's in the interface of Blender. He's working with Blender at the interface of the program. And now in a 3D, in a full 3D model. And we are now at this point, we are just starting to simulate what we have to simulate at the virtual contest for his master dissertation. Of course, there are some works that question the use, some limitations of FAIR. Usually fragmented component parts of the organisms are available, blah, 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 but we know that. But again, it's what we have. So we have to deal with all of these limitations to get to something like this and try to answer as better as we can. E meu café ficou frio, né? So again, this is the limitations, and here, this is my work specifically that I had commented at the beginning of the presentation, the testing, the optimal stance of Anhanguera piscator on land. It's a quite interesting work because it handles both with 3D modeling and math. So we work with Anhanguera piscator now, again, a 3D preserved specimen, so not a 2D specimen. And we worked at the virtual contest determining the centroid, femoral centroid, to articulate the femoral head with the acetabulum. So different from what we had at the beginning with manually. So now the program do it. It calculates the center, and from this point, we articulate at the acetabulum and fix it in the articulation, and the range of movement is made by the software. So we established all of this. This is in a mesh of the bones. And this is the interface. We worked with 3D Max. That is similar with Maya. And then we had to reconstruct, of course. The bone model alone is nothing, because bone alone doesn't move. So we had to reconstruct all the muscles, integrate all the muscles, and we have this technique that we use, that is extant phylogenetic bracket, that we use the closest taxa, extant taxa, to fill these gaps and reconstruct muscle of extinct organisms. Here we use crocodilia and aves, of course. So we use it to reconstruct, compare and reconstruct muscles at our specimen, and use this formula of a lever arm. This is the formula of lever arm. It's a quite simple formula. And we established these values to all the range of movement possible for the femur. And these are the graphics that were produced from these calculations. And here is the bone model that articulated and with the muscle spots of all groups. And it's a 3D round with the model complete, with all the muscles, all the lines. These spots, they're created lines to join the origin and the final spot of the muscle by these lines. And then, after calculations, we have reached this optimal position, angle position for these bones, and we repositioned our model to this, according to our results, and then this was the final posture. So it was a quadruped, not a biped animal. So this is the repositioning of the model from, this is a plain model without the movement, and here is this model repositioned with the angles that we have found. And here is the stance that we could prove mathematically for this specimen. So it's not a biped, but it's a quadruped. And this is a quite interesting thing, that because of our work at PUC Minas Museum, they had in Piscator the exhibition that they repositioned according to our work. So I liked it. And then we have this Rodrigo that is here. Rodrigo, yeah. And Rodrigo is working with us and started working at the master dissertation with also 3D modeling and these forces in reconstruction. In this case, a bite force estimation in pterodactyloid pterosaurs that culminated in this article that I have mentioned before. That was the first attempt to reconstruct the adductor musculature of the pterodactyloid skull in detail, and used the osteological correlates and EPB method, the extent phylogenetic break method. So it was nine species used to estimate bite force, and the implications for potential dietary habits were also performed and investigated. So here are the specimens, all the reconstruction that was made regarding this muscle for the species here, and comparisons between them, and the graphics that compare the bite force, the absolute bite force and bite force quotients for these analyzed pterodactyloids, all of them plotted here, and the results that we have reached that the biomechanical performance of pterosaur jaws are related to feeding styles. Of course, from this study, more things can be refined, implemented, of course, but it's a quite interesting study that copes with 3D modeling, muscle reconstruction, comparison, and answer to a question regarding biomechanics, that's bite force, related to feeding behavior. So, of course, finding details of jaw shape variation could capture stronger biomechanical signals, for example, but of course we have to further investigate it, but it was a very, very and quite interesting work. And now Rodrigo is finishing his PhD thesis, working with the biomechanics of wing stance during flight in Anhanguera piscator et Tupuchuara leonardi, and he's going to the consideration of flight evolution in the group. Here's a tomography of the Anhanguera humerus. We used Aviso for this. And a photogrammetry of the Tupuchuara humerus using Agisoft. Here, all the photographs that were compiled to do this model. It's interesting to note, it's worth mentioning that we went to Japan to see the piscator and do all the photogrammetry and produce the model. So it can be quite expensive, but it's good. Here is the model and the reconstructed muscle lines at the 3D wing model in different views. Of course, these lines were also reconstructed using EPB method, the extant phylogenetic break method. Here are different views of this wing. Other view, he uses the OpenSim, it's another software, and the complete articulated wing of piscator in anterior, dorsal, and ventral views with Blender. Now we are going to start and finish the simulations of these, and we'll get some results soon. And of course, when working with flight, we have to understand how these forces are applied over our animals. So we have to study physics of the physics of flight. So we have a lot of forces involved, like angle of attack, chord line, camber, and drag. So we have to, but now we are going to deal with it with our model to see what's going to happen. So these are the forces that we have to consider when flight. And that's it. I think now what we have here at the lab. So we have 4 granted scholarships of FAPESP that came from a project that was approved last year. And with this project, 4 scholarships came with it. And of course, in red, there are those that are related to pterosaurs, but the project was dealing with reconstruct 3D modeling in in fossil vertebrates. So we have worked with Notosuchia, we are working with crocodilians as well, but we have a scholarship for master and doctorate using pterosaurs, basically dealing with flight. That's our interest for now. And also scholarships through the program, the regular selection, that is, it happens every year. With these issues, this is a theme that we are going to work, a kinematic analysis of pedal movement in non-pterodactyloid pterosaurs and its influence on the selection of arboreal microhabits, because they, you know that this is not a non-pterodactyloid, but some pterosaurs are figured in trees and with this kind of behavior, and we are going to test if they could do it biomechanically. And another theme, another issue is the binocular vision analysis in pterosaurs for a PhD. So that's it. And we are with a partnership because of this project with Professor John Hutchinson from the Royal Veterinary College. So we hope to learn a lot, better and better, how to deal with these difficult softwares. And of course, here I would like to leave here that at UFABC we have an equipment park that's quite developed with a lot of equipments, and they say, come and use it, because we have to justify this equipment here, and it's expensive to keep. So they have a lot of different microscopes, math, softwares from the engineers that we use. So if any of you need partnership, is very welcome. We can help and go there. Please use it. Our structure is available. And that, I think my purpose here is not to, wow, it's a lot quite of math and computer and numbers, but it's the reality of doing biomechanical studies with this group and with other groups. But so it's just to show you a little bit about our reality and the problems that we have to deal with, and the advances that we can reach doing it. And now specifically, it's the big challenge is doing with AI that we are trying to learn and teach the machine to do what we want. So here's my contact. Thank you very much.
Thank you. Sorry. Thank you, Fabiana. It's not my fault. It was not my fault. Sorry. Thank you, Fabiana, for your presentation. Congratulations on your presentation. And does anyone have any questions for Fabiana?
Thanks.
Thank you, Fabiana, for this very nice presentation. I just have a very general question, and that is, when you say it's expensive, you know, what is expensive? 1, 10, 100. So I was just, I don't know what I'm doing. I don't know if it was Renan who has something to do with that mic. Okay, let me just, anyway, how much overall is from the start, and I'm not talking about fellowships, I'm not talking about electricity or a new mic, from the start to the end, how much is such a study around, just to give a bald picture in terms of finances?
Just to give you an idea of one equipment that we can use, we got the money for a 3D scanner it's a medium one of 50,000. 50 reais. No, dollars. No. Yes, but it's not the most expensive one. It's a medium equipment. So, if you can consider the cheapest equipment that is to photograph, to take photographs, to have equipment you can have I don't know how much the good equipment that Canon or costs nowadays, but a good one with a lens, kind of 5,000, 10,000, at least, more or less. So I think from this 10,000 with the up, I think it's the minimum.
But we know we have the NCT.
Yes.
That's coming at time.
Yes. And then we can invest on this equipment. It is quite interesting because we have money for it. So we are on the top. Can be. Pode fazer em português.
Você tem alguma relação, assim, posteriormente de fazer a fotogrametria e trabalhar com digamos, a biomecânica do voo e depois, posteriormente, fazer uma impressão em 3D desse material ou alguma coisa assim, em relação à biomecânica e a impressão em 3D através das técnicas de fotogrametria? Você pretende, né, um dia fazer isso?
I think in this case, it would be the complete process. For now, when we talk about 3D, we are talking about doing it for exhibition purposes. But like the engineer said, it would be quite good to validate with these real models from these virtual models to test them at the real world, because of course we simulated the virtual world, but in the real world, we know that things can work differently. So I think we can consider it. Of course, it's another cost because 3D printers have a cost, but we can try to do this reverse step to produce these models and together with the virtual model, test them and see if we get the same results. But we did not try to do it. What we can, I think it's the full process. It can be considered. That's my opinion. But it's more, yes. All about money. But the 3D printers are like these equipments. We have the cheap equipment and the most expensive one. Depends on what we want, what quality you want, the type of the model. We can have a lot of structures. You have to get better equipment. If it's a simple model, a cheaper one is good. So it depends. So we have body goes. Let's study biomechanics.
Let's study biomechanics.
This is the last talk.
So thank you, Fabiana.
Thank you.
Just to announce again that the location for our happy hour has changed. Instead of being in that bar that we were last night, it's going to be in a different bar, which is walking distance 1 kilometer from here. You guys can either walk or Uber or taxi. It's called Nona. You can check in our schedule for tomorrow. It's the same bar we're going tomorrow night. So we are gathering there tonight as well. Okay? At 7 p.m. So that's it for today.